Lab Project M5, buffering I/O. This is a practice that's very common with PLC PAC programming. It's not necessary for all platforms, but it's good practice. And the concept is to avoid asynchronous behavior, meaning when the program starts to execute, rung after rung after rung, in the rungs, it is examining, on occasion, input bits. In other words, bits in memory locations that are associated directly with a screw terminal, an input. And it continues to look at those different inputs as it goes down through the logic. Some platforms update that image asynchronous. What we've described before is collect the inputs, execute the logic, setting the bits in memory identified as outputs, and then transferring the outputs out to the real output devices. There are many platforms that the inputs update the memory locations asynchronous, meaning they can do it at any time. They can do it on a regular schedule, not just at the beginning of the program. In that case, an input, a value for a bit in memory that represents an input, could change state between the first rung and the last rung. That would not be good. Now, you don't have to learn this for Micro 800 necessarily, but remember, when you get a job out there, or if you already have a job working with PLCs, PACs, you have to work with the installed base. That means you have to work with everything. So if you run across buffered I/O, you'll look at this after doing this lab and know exactly what's going on. And basically what we're doing is we're taking all the embedded I/O and we're rung by rung copying the state of that embedded I/O module-defined data type bit into a global variable data bit that we created. And we do it at the beginning of the program. And then when we're running the program, instead of using the embedded I/O bits, we use the other bits that we move the embedded I/O state into. Those only get updated on the very first program, and then in the program we don't directly change the state of bits associated with output devices. We change another bit that we created. So all those bits get changed for outputs going down through the program, and when you get to the end, then we take and copy the state of those global variables that are not output bits. We copy them over to the real output bits, and out they go to the outputs, which means that the program is totally isolated from any changes in I/O except at the very beginning for inputs and the very end for outputs. Real simple lab project. I'm telling you, there's nothing to this puppy. So let's go ahead and do this. If you've already done this lab project, keep listening to the lecture. If you haven't, you may want to pause, do it, and then come back or watch it again. So let's go look at this. The very first instruction, step 1 in M5 of the second edition, gave you an involuntary learning experience because the text should have read, create a new project as buffered I/O, or giving you the choice of deleting everything in your current project and then rename it as buffered I/O. And primarily the reason for reusing the older program but cleaned out and renamed is so you didn't have to redo the connection path. In other words, you didn't have to go back and redo RS links and establish communication between your computer and the simulator. If you do create a new project, and remember in the manual you're seeing Micro 810s, Micro 820s, and Micro 850s, whereas in this set of lectures you're only seeing the Micro 850 simulator. When we chose our processor over here, see Micro 850 Sim. And by the way, some of the really tight step-by-step, every T crossed, every I dotted procedure that we did in the first labs, we will not continue to do. We're going to assume that you've learned how to do these things, and we'll just say go offline, edit your program, and then download it and test it. So we're not going to go step by step. We're going to start reducing that. That gives you a chance to exercise what you've already learned. This involuntary experience, hopefully when you look closely, you saw that there were no programs until you created one and named it buffer inputs. So we're going to right click on programs, add ladder diagram, and then we're going to go back here. You can just click on it to bring up the edit field, or you can right click and rename it. And of course you have to have an underscore for a space. You can't put a space in a program name. Ideally, what you would have done when you discovered this incongruity here was to delete the program that you had and to clean up the tags, bit 1, bit 2, 3, 4, 5, etc., and then more or less start from scratch. So this is where you should have been more or less at the beginning of this lab project. I do want to say something about why we are concerned about buffering the I/O. Buffering means to put it in a temporary place. This has become an important concept with some of the newer controllers. Now this particular family of controllers, it's not quite as critical because they are more synchronous than, say, control logics and compact logics, which are totally, for the most part, asynchronous. This has to do with the I/O. The original PLCs, and you saw this in the earlier lecture, you might want to go back and review this if you forgot it, is that the sequence is that it goes out and it gets a snapshot of the voltage levels on the screw terminal via the opto isolator. So really it's not going out and capturing 24 volts, but it's going out one module at a time to see the on or off state of groups of inputs. So it does it in groups, so you can say it takes a snapshot, so to speak, and then puts it at a specific location in memory that you're going to use as the state of those inputs. Then it executes all the logic in your programs. Then it takes any output memory locations that have a DO instead of a DI. By now you've used at least one of those. It updates those at the end of the program scan. In other words, those bits are set during the program scan. Output bits are turned on or turned off as a result of your logic. Then when you're done scanning all the programs, then it takes those memory location states and transfers them out hardware-wise out to the actual output opto isolators, hence the screw terminals, operating devices. That is synchronous. It's the fixed scan cycle every single time. Now there's only one variation to that, and that is if you use selectable timed interrupts, and we're not going to discuss those right now. What that allows you to do is to do a periodic program run. In other words, you can set up a program so it runs periodically. This is appropriate for proportional integral derivative instruction, the PID instruction, because a couple of those elements in the PID relate to time. In order to get an accurate calculation, because what a PID instruction is, it watches a variable like a temperature of a tank. It looks at the set point that you provided. It generates an error, and then that error signal generates a change in the output variable, to increase the power going to the tank or decrease the power going to the tank to either heat it up to the set point or cool it down to the set point. And because there's a time element involved in two of these PID elements, having it very predictable is an advantage. Not totally necessary. However, aside from that, these controllers are, for the most part, synchronous, whereas with control logics and compact logics, most of those modules, especially for control logics, have a second generation RISC processor in them. So every single module in a control logics chassis is a computer in its own right. Even an input module, 16-point input module, it has a processor, and part of the setup for control logics processing is what's called a requested packet interval, where when it boots up and goes online, it goes out and tells the modules that they are going to come and update the input image on their own. The processor's not going to come and get it, which means that if you set up RPIs, requested packet intervals, of different, millisecond increments, 20 is pretty much the standard, that the I/O is going to get, your I/O input memory is going to get updated at that rate, not at your scan rate, so it becomes asynchronous. Remember, we're learning PLCs, not just learning how to program a Micro 800. So we include all of these concepts into our course. Now we're going to show you two forms for buffering inputs. The first one, we're going to take an integer and then use the individual bits as the buffer for the state of an input, and then we're going to do the same thing with an integer for the outputs. So let's continue on here. So we needed to add a rung after we added a tag. So we went into global variables. Let's double click and open up program. We have a rung. There's two ways you can do this. You can go create the tag and then do the rung. I think I had you go to global variables, go down to the bottom and type in IN, but don't make it a Boolean, make it an integer. Now, why an integer and not a double integer? Because a double integer is probably the native data type for the memory in these controllers, at least the 820 up. I'm not sure about the 810. Well, 16 inputs is more typical of an input module, but you could do a double integer if you were buffering inputs for one of the 32 input DC digital modules. Keep in mind that the method I'm going to show you right now is not my preferred method, but it is the quickest because you simply go in and create a global variable called in. Then we go back to our program, we drag down a true if on or direct contact. Then I'm going to go up here and type in IN, and then I'm going to put in a decimal point. The instant that I do that, it opens up the elements of the integer that we named in and shows us 0 through 15. So I'm going to pick input 0. Before we add the OTE, let's create the variable. So we go to global variables, go down to the bottom, and we create one called out of the integer type. Go back to the program, drag in an OTE, and I'm just going to type in OUT. See, it comes up here, and then I'm going to click on it, decimal point, and then output 0. Okay, so now we have a rung that uses an internal bit to control another internal bit. So bit 0 of the integer in is controlling bit 0 of the integer out. Then we had you save and download. And before we download, of course, we have to turn on our simulator. That's one thing that sometimes you forget about because I'm more accustomed to doing this with a real controller. I tend to just go ahead and download because I think I'm already connected, but in this case you're not. So we'll turn it on. We're in the run mode. Now we can download. When this comes up, I'm usually picking download with project values simply because I'm not trying to maintain an as-built program file for the machine on the shop floor. If I was on the shop floor, I have a whole different scheme for how I work with the online and offline files. So download with project values. This always takes a minute. And once it does, then we can... Okay, here we are online with our single rung and logic. And remember that we have just 2 bits in play here out of 2 integers. That's all that's going on here. This has nothing to do with I/O yet. All that we did was showed you that you can take and use a bit from an integer, read it with a true if on, and then write to a bit in another integer. So this logic runs just as you would expect it would. That was all there was to this first step, was demonstrating that this rung functions. Then we had you save and disconnect. By the way, there was a question in there. Does this logic function correctly using these new types of bits? Yes, of course it does. Then we had you save and disconnect. So we're back offline. Then we had you edit the rungs. And since we're fairly new to this, I'm going to go step by step. What I'm going to do is I'm going to bring down a rung. I'm going to bring down an OTE, energize output, and I'm going to name it input 0. Now we already have input 0 here, so I'm going to type in IN decimal point 0, and then I'm going to bring down a true if on. I'm going to go to I/O, and I want digital input 0 right there. So I'm using this bit in memory to turn on that bit in memory. This bit is controlled by a screw terminal logic level or voltage level. This is just an internal bit. So I'm basically taking the state of this input and I'm buffering it at this temporary location. Now I'm going to take and type in OUT decimal point, output 0, and now I'm going to underscore IO and kind of get the thing typed forward. And there it is, digital output 0, enter. Okay, now I had you save this and download it. Download with project values. And here we are online with our logic. And I had you toggle input 0 on, which you can't do because it's an input, right? So we have to go down here and bring our simulator into focus. Click on input 0, and that turns on input.0. Then I had you toggle this on, and if you look down here at the controller, you can see that input 0 is on and output 0 is also on. This is just one more step in the process. So we see here IN.0 has the same value as this input memory bit, and this output memory bit has the same value as OUT decimal point 0. So that's part of the sequence. Now let's go save and go offline. One thing to point out that these are equivalent only in the run mode. If you're not running, then the processor doesn't read this memory location and write to this one. It doesn't read this memory location and write to that one. So these are equivalent states, but only in the run mode. So I just save and disconnect, and then add another program called sequence. So we go up to programs, add ladder logic diagram, click on it, name it sequence, then we open it up, and in this program we added a rung that looked at, and I'm going to cancel this, I like to do it right here, and notice I typed in lowercase, okay? You don't have to hold down the shift key. You can just type in lowercase in, and when you hit decimal point it comes up with the elements. So we pick that one, then we drop down an OTE, type in lowercase OUT. When you hit decimal point, of course 0 is the first one up, so you can just hit enter. Then at this point we had you save and download again. We're doing this in steps, and you're getting a lot of experience with saving and downloading. Not much with uploading yet. Our logic, our instructions are already on simply because we left it in that state. If I turn off input 0, notice that output 0 goes off. So these are the real inputs right here, down here in your simulator. 0, 0, that's input 0. You can read the tag name, the variable, and down here is the output. If I turn this on, that output goes on. But this is not the input, and that's not the output. We've buffered those. In our buffered inputs, and by the way, this is a buffered output. We're going to fix that in a minute. You can see that if I turn on input 0, it turns on this bit. But nowhere in this logic do you see what's turning on output 0. That's in this other file, program file. Now we don't want to leave this output buffer in the input buffers program. So we're going to save, disconnect. We're going to create a new program. We're going to call it buffer. And by the way, you can use lowercase, buffer underscore outputs. So we could have left out the underscore and it still would have been readable because you use the capital letters as your delimiter between one word and the next. And then we take, and because I'm a chicken, for something like this I wouldn't be worried about it, but as general practice I copy, paste, delete. So I click on that, right, Control C, and then I go to buffer outputs, paste it in there. We don't need this rung. Then I go back to buffer inputs and I delete this rung. So now in buffer inputs, I'm buffering input 0 into IN decimal point 0. In other words, element 0 of the integer IN. In my sequence, I have a rung that reads IN.0 and writes it to OUT.0. Then in the buffer outputs, I take OUT.0 and I control the state of this digital output 0. So this is the typical layout for most programming these days. People buffer their inputs and buffer their outputs. And in between the buffered inputs and the buffered outputs, they have their program file, their actual logic. Now again, the reason that we're buffering is because if you do it this way, the very first program that executes is buffering the inputs. It takes, we'll go to that one, it takes the state, and by the way, we're not done with this lab yet. It takes the state of all the inputs and buffers them in a, we'll say, a temporary location. But this program won't get executed again until the processor's gone through all of the programs, updated the outputs, done the housekeeping, and then come back and does it again. What this does is prevents this bit from changing state because this bit changed state during the program scan. Now with this controller, you're not really worried about that. But with control logics and compact logics, that's not a remote possibility, that's a definite possibility. And when you write your code, you may not realize this yet, but as you go down and write your code, because of how the scan is sequenced, you are depending on any input staying in the same state as far as your program's concerned for the whole program scan. They might be changing at the screw terminal, but that doesn't show up in your memory until we do the input scan. Now remember, the other processors like control logics, compact logics, they use the requested packet interval. Those modules on their own hook come and update the input memory locations anytime during the program scan. That's asynchronous. Okay, and so that's why we're teaching you this here to buffer your I/O. This is in the very first program that's run. So you use this as your input, not this, because you know this can't change regardless of what's going on out there on in the field wiring until you get all the way through sequence, buffered outputs, housekeeping, and then back to buffered inputs again. So the last thing we had to do more or less is click on that rung, Control C, and then Control V 5 times. 1, 2, 3, 4, 5. So I'm going to click on this, double click there, click on this, double click there, click on this, double click there, click on this, double click there. Now where you get into a little bit of trouble is you see it only goes down to 8. So when you get to 9, you're going to have to go over here and scroll down somewhat. So I've got 0, 1, 2, 3, 4, and then 5. Okay, that takes care of buffering your inputs. Now let's do the outputs. So select the rung, Control C, Control V, 1, 2, 3, 4, 5 times. Now in the manual, you only did 4. But because we're using the simulator, and some of you may have a 20, a 30, a 50, or a 70, and you're using our digital field device simulator, you've got 6 in and 6 out. So I'm going to do all 6 out. So it's the same thing. Click. Okay, you get the gist. So now I have 6 inputs buffered into this single integer. It's not a single integer, it's an integer, 16-bit integer. I'm using the first 6 bits. Now there's another way to do this, which I prefer better. I'll show you that later on, but for right now, you get the drift of buffering I/O. And then I had you go to sequence and put something in a little bit more interesting. Drop down and you can always duplicate these rungs just like we did before. So we need, I'm showing 4 rungs because the Micro 810 has 4 outputs and that's all. I'm going to do this a little bit different. It's still going to work out the same. So what I'm going to do is copy this, Control C, and then Control 1, 2, 3, 4, 5. Then I'm going to go here and then here I'm going to now we have a situation that we can't see all of our rungs of logic. I can drag this down so we can, and then drag this over out of the way. Now we can see all 6 rungs. However, when I pop up the simulator, then we can't. So I'm going to turn off input 0 so you can see that it's still functioning. Input 0, input 1, turns out output 0 and output 1, because this is a common condition to both. So if I turn off 0, then only output 1 should be on, correct? As you can see. Now I can move this out of the way temporarily. So I want to turn on input 2. See, it turns on output 2 down here. I can turn on input 3. That turns on output 3. 4. It turns on 4 but not 5. If I turn on input 5, then it turns on output 5. If I turn 4 off, then 4 and 5 both go off. So we've done several things here. We showed you how to create additional programs, and we did put them in an order that we want them executed. Buffer inputs, do the sequence, buffer outputs. That is the typical PLC scan. In the buffer inputs, we took the state of the screw terminals. We'll just turn all these on right here. That's 6 of them, 0 through 5. We go to buffer inputs, bring the simulator back up, and you can see that if we change the state of any of these input screw terminals, it changes the state of its coordinated internal bit, or its buffered bit. And then as far as the outputs go, they are at the mercy of these bits, and these bits are controlled in the sequence. So this is your program right here. Those other 2 are not. The buffer inputs and buffer outputs program files are not your sequence or program for your machine or process. This is. Those are simply there to guarantee that the inputs or the values that you're using to represent inputs do not change while you're going through the scan of this logic right here. Now this is so small and it would happen so quick that I doubt that you could detect any difference no matter the circumstance. But we're teaching you concepts that you're going to use in the future. And the last thing we had a logical statements of review. And we had you look at like rung 1 here. And there's many ways you can read this. If input dot 0 is on, then this is true. And if input dot 1 is on, then this is true. Therefore the rung is true. Write to output 1 and on. Turn output 0 on. So I had you go down and kind of write out the logical statements. Now the way it's actually stated in a true-false sense is input 1.1 is on. That's a true statement, so this instruction is true. So it writes a 1 to output 1. Input dot 3 is on. Well, it's not, therefore this is going to read false and turn off that bit. Because remember, these OTEs or direct coils, they all have a true execution and a false execution. So 5 of these rungs are true. So 5 of these OTEs are executing the true execution. We have 1 that's not. It's executing the false execution. All instructions are either conditions or actions. Conditions are always true or false, never on or off. Now you can look at this. This is a true if on, and you can look at its state and say, oh, that must be on. That bit is on the memory. But that's not what this is saying. It's only saying it's true. It's the fact that you can read it as a true if on, therefore, if it's true, then that has to be on. But these are all true and false over here. These are the colors displayed represent on or off. In other words, the fact that this is red and it's on, what if we put in a true if off instruction? It would be false when that input is on, correct? So over here, make sure you're thinking true and false, never on or off. Over here, what is displayed color-wise is on or off. As I said, some have a true execution and a false execution, like the direct coil. Some have just a true execution and no false execution. Some have a false execution and no true execution. And I will show you those in later labs. As I said, this lab project was very simple. Now what you have is a program that primarily has a buffer inputs program, a buffer outputs program, and then something in between, maybe called a sequence. And that's where you would put your main program. I would save this with nothing in any of the program files except for buffer inputs and buffer outputs. I would save this as a template. That way, anytime you want to do a project where you have the I/O buffered, you just open this up, save it with a new name, and then start throwing your program in there. You're also going to find it easier to write your programs when you can use IN00 instead of underscore IO underscore EM underscore DI underscore 00. To me, that's a pain in the butt. I'd rather use IN00. So that's it for buffering IO. Let's move on to the next subject. We'll see you for the next lecture.